Welcome back to the second half of the video guide on how to solve self-study exercises, number 3. So I've just started doing problem 2. We have to write electron configuration of the following species, and we need to use a shortened noble gas abbreviation if we want to. So the first item or the first element is copper. I quickly find copper in the periodic table. The atomic number is 29, okay, so we can write that down. Okay, 29 electrons. The noble gas that we are going to use for copper is going to be the one that stands before copper. So the one that stands before is argon. Okay, argon, 18 electrons. The remaining electrons are 4s1, 3d10. Please bear in mind that there's a special stability of half filled or fully filled d orbital, and they're more stable than the partially filled d orbital. So therefore, such a configuration as 4s2 and 3d9 for copper is incorrect. Okay, it's not going to exist. Now, how do we write electron configuration for copper plus then? Is simply electron configuration for 28 electrons, okay? And the electrons that are lost in the first instance by transition metals are the 4s electrons. Hence, I will end up with just 3d10 electrons, removing this 4s1 electron. Okay, the next one is copper 2 plus ion. Because we run out of 4s electrons, we then remove one of the 3d electrons and we end up with 3d9. The next element is chromium. Again, quickly refer to periodic table. Atomic number is 24. So 24. I would use again argon and then 4s1, 3d5. All in total 24 electrons. Cr plus is the similar trend. I'm going to remove one of the 4s electron and then I end up with 3d5 electrons. Okay. Now the next one is manganese 2 plus. If I refer to the periodic table, as a neutral atom it has 25 electrons. So if you want, you can quickly write electron configuration for 25 electrons. For a neutral atom, have 4s2 and then 3d5. Now removing 2 electrons, we will end up with just 3d5. Okay. The next one is zinc 2 plus. Similar, zinc atomic number is 30. I would write argon and then 4s2 and then 3d10. Again, when we knock out 2 electrons from neutral zinc, we will just end up with argon and then 3d10. Okay. The next one, by referring to electron structures, explain why the second ionization energy of both chromium and copper are higher than those of the next element. Okay, the next element, it means the element that stands after the chromium, for example, and copper. Okay, so in our case it would be manganese and zinc respectively. So if I compare the first pair, chromium and manganese, and copper and zinc. So in order to solve this type of problem, I usually guide students to first draw the electron in boxes configuration, which is we've already wrote electron configuration for chromium, which is this. It's 4s1 and then 3d5. 1, 2, 3, 4, 5. Each 1 electron in each orbital. 3d5, 4s1 versus manganese is what? 4s2, 3d5. 1, 2, 3, 4, 5. This is 3d5, 4s2. Now, when we talk about the second ionization energy, we first have to mention the first ionization energy. So the first one would be to remove one of the 4s electrons for chromium and for manganese. No difference as such. The second ionization energy or the second ionization process would be to remove, for chromium, it would be to remove one of these 3d electrons in a half-filled special stable orbital. Okay, one of these 5 electrons, whereas for manganese it would be simply the second 4s electron. Therefore, in order to break this stability, you need to supply much more energy, okay, compared to one of the 4s electrons, right? The similar explanation should be given for copper and zinc. Okay, for copper we already see its electron configurations 4s1 and then 3d10. Okay, so we have fully filled 3d orbital, and for zinc we have the same fully filled 3d orbital, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 4s2. The only difference is that we have 4s1 electron and 2 4s electrons, okay, for zinc. Now, when we compare the second ionization energy, we can see that the first ionization energy is again to remove one of the 4s electrons for copper and one of the 4s electrons for zinc. Now the difference comes for the second ionization process, whereby in copper the second electron would be removed from one of these 3d electrons from a fully filled d orbital, which is very stable, compared to zinc, whereby the second electron here is removed just from the 4s subshell. Okay, therefore again much more energy would be needed to actually overcome this stability, or to break the stability. Okay, now the third one, or the second question, sorry, the third ionization energy for both manganese and zinc are higher than those of the next element. Again, if we refer to a periodic table, manganese would be compared with iron, whereas zinc would be compared with gallium. Okay, manganese versus iron, zinc versus gallium. Again, similar procedure as here. You have to draw the electron boxes configuration for manganese. It's already here. It's 4s2 and then 3d5. 1, 2, 3, 4, 5 versus iron, 4s2 and then 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. Okay, so this 3d6, 4s2. Okay, if we now consider only the third ionization process, we first remove one of the 4s electrons, then the second 4s electron, and then the third electron would be removed from this again fully half filled 3d orbital. Okay, and for iron we are going to remove one of these paired electrons. Okay, so we have a pair of electrons here that actually repel. Therefore you don't need to supply so much energy here to remove one of these electrons compared to one of these unpaired electrons in this orbital. Okay, in this 3d subshell. All right, now let's consider zinc and gallium. Okay, for zinc it's already here, so we can just redraw if we want to. We have 3d10, 1, 2, 3, 4, 5, so fully filled 3d orbital. Okay, compared to gallium, which has also 4s2, then again fully filled 3d orbital. Okay, and it has 4p, one of 4p electrons. Okay, So now if we compare the third ionization process here, for zinc it's going to be one of these 3d electrons, okay, but for gallium it's going to be the 4p electron, which is higher in energy, and hence it would be relatively easier to remove this electron compared to one of these 3d electrons in this fully filled d orbital, okay. And the final question is to compare the radii of the species in A to C, D to E, and F to G. Okay, so if we compare the species A, B, and C, we clearly see that we have a neutral atom copper, positively charged ion copper plus, and copper 2 plus. So when we form actually copper plus ion, we knock off one outer shell electron from copper, and by doing so we actually reducing the shielding effect, okay, from the inner electrons that exist in copper and that the outer shell experience. Therefore, when we reduce this shielding effect, the outer shell, the electrons are held in copper plus ion are more tighter than in neutral atom, and even more tighter if we remove two more electrons, okay, because the idea here is that the number of protons still remains the same, okay, so the nucleus attraction is actually stronger here because it's attracting fewer electrons and even more fewer electrons, okay. So because of that, the size of these ions would be smaller than its corresponding atom, okay. So if I say that the smallest one would be copper 2 plus, then copper plus, then, the smallest one would be copper 2 plus followed by copper plus, and the biggest one would be neutral atom. The same explanation can be applied to D and E. So chromium would be bigger than Cr plus, and then the final one is the manganese 2 plus and zinc 2 plus. Okay, if we compare these two, they are in the same period, okay, manganese and zinc. Zinc has a greater or bigger atomic number, so it's going to be a smaller particle, a smaller species than manganese, okay. Alright, okay, thank you for watching, that's all.